In this lesson, we are going to look at the transformations of exponential functions using the graphing method. Just like we saw in Unit 2, we still have A, B, H, and V representing the different transformations that we can apply to the function. But now we are going to apply them to the exponential function. In Unit 2, we spent quite a bit of time recognizing the base functions and being able to identify which base function you would graph before applying the transformations. So remember the quadratic. The base function was x squared. The square root function, we had to see a square root. The absolute value function, we saw the absolute value bars, and then we had the reciprocal function. Exponential functions have the form y equals some number that we call k to the exponent x. So our unknown is the exponents, and k will have to be given to you as a number. So it could be a whole number, such as 2 or 3 are quite common, or if it's a decreasing exponential function, it would be a fraction, such as 1 that's less than 1, such as a half or a third. So k is your base of your exponential function, and that's going to help you graph your original base function. Then you are going to look at the parameters a, b, h, and v and apply those to your original base exponential function. So a quick reminder, just in case you forget, A will help you identify the vertical stretch or compression, and also if there's a reflection in the x-axis. B will tell you if there's a horizontal stretch or compression, and also if there is a reflection in the y-axis. H will tell you if there's a horizontal translation, and V will tell you if there is a vertical translation. And just as before, you have to be careful with B and H. Often we'll put brackets around that entire exponent. B and H affect your x values, and they are in the bracket of lies. We will do two examples. The first one is for exponential growth, so when the exponential function is increasing, and the second example is exponential decay, when the exponential function is decreasing. So in example 1, we are given y equals negative 3 to the exponent 1/2 x plus 4. These brackets really are not necessary. Doesn't matter if they're there or not. You could write this as y equals negative 3 to the 1/2 x plus 4. Part A asks us to identify and graph the base function. So the base of this exponential function is 3. It's that large base number there, 3. So we will say the base function is y equals 3 to the x. So to graph that, I'm going to start at an x value of negative 1. 3 to the exponent negative 1 is 1/3. So I'll point around there. And then I will do when x is 0, 3 to the exponent 0 is 1. So I have my y-intercept at 1. And then I will do an x value of 1. 3 to the exponent 1 is 3. And then I will do at an x value of 2. So you will substitute in 2 for the exponent. 3 squared is 9. And now I'm off the grid. My next point would be when x is 3, 3 cubed is 27, which is quite a bit of ways off the grid, so I'm not even going to kind of just plot it above. That is as many points as I can plot. So I have joined those points together, and I have labeled it. So that is my base exponential functions. Now I'm going to identify a, b, h, and v, and then transform this graph. So the a value is the number that's being multiplied outside the function. So we see we have a negative, which represents negative 1. So a is negative 1. Because the absolute value is 1, there is not a vertical stretch or compression, and the negative tells us that is reflected in the x-axis. The b value is what is being multiplied to x. So in this case, it is 1/2. Remember, this is in the bracket of lies, so that means there's a horizontal stretch of factor 2. The h value is being added to x, also inside the bracket of lies. Just do a quick check to make sure this is in factored form, which it is. So h is the opposite sign. So h is -4, which means there's a horizontal translation 4 units to the left. V would be the number that's being added outside of the function. So here there is nothing being added or subtracted. So we would say that V is 0. So now we will go and graph the transformation. Remember, we're going to do this in 2 steps. We're going to apply A and B first, and then we will apply H and V. So we will stretch before we move. So I've decided to start at this point, 2, 9. A reflection in the x-axis will bring that point down here at 2, -9. And then it's a horizontal stretch by 2, which means I will double the x value. So an x value of 2 becomes an x value of 4. Also, you're doubling the distance away from your y-axis. So that point goes here. The next point at 1, 4, I'm going to reflect it. So it's at 1, -4, and then I'm going to double the x value. So it's at 2, -4. And then this point here at 0, 1, I'm going to reflect it at 0, -1. And because I'm on the y-axis, when I do a horizontal stretch of 2, it will not affect the x value. And then this point here at -1, 1/3, we'll reflect it at -1, -1/3, and then I'm going to double the x value. So instead of -1, it's now at -2. So I have transformed all the points on my original function. I've joined them. The equation is y equals -3 to the half x. The negative because that's my a value, which I applied, and the half because that's my b value, which I applied. One thing I should mention is an exponential function does have an asymptote. It is along the x-axis, which has an equation of y equals 0. Stretches and compressions, vertically or horizontally, do not affect asymptotes. So when I've done this transformation, it still has the asymptote y equals 0. Finally, I'm going to apply my h value of -4, which means all of these points are moving 4 to the left. My v value is 0, so I'm not going to move up and down. So I have moved all the points 4 to the left, joined them, and wrote the final equation. And again, the asymptote has just moved to the left, so it's in the same place. So my final function also has an asymptote at y equals 0. So one thing that we should also just quickly talk about is the domain and range. The domain of exponential functions are always x is an element of all real numbers, and the range, now that we have been reflected in the x-axis, the restriction on the range is y is less than 0. In the second example, we see that the base is 1/2. That is where the exponent is. So I will say that the base of the function is 1/2 to the x. So this 1/2 is not a transformation. It's just going to tell me what my original function looks like. And because my base is less than 1, I have a decreasing function. So when I graph, I am actually going to start at -3. Because when I put in -3 here, the negative tells me to flip the base, so I get 2. 2 cubed is 8. So when x is -3, I get a value of 8. And 8 can fit on the grid, so that's why I started there. If I went to -4, I'd actually get a value of 16, which is off the grid. So you want to fill in your grid space. The next x value I'm going to go to is -2. 1/2 to the -2. Again, that flips the base, so it's actually 2 squared, which is 4. The next x value is -1. 1/2 to the -1 is 2. The next is when x is 0, so I'm going to put 0 there. Any base to the exponent 0 is 1. And then finally, I just want one point on the other side that's close to the asymptote. So I'm going to choose a value when x is 1. 1/2 to the base 1 is just 1/2. So I drew the exponential curve and labeled it. And just remember, if you do have 1 over 2, it's just a reflection of 2 to the x in the y-axis. So if you know what 2 to the x looks like, which is a little easier to do in your head, the y values are just the opposite sign. So it's just a reflection in the y-axis. So now we are going to take a look at the transformations. The first thing you should notice is that the exponent is actually not in factored form. So that's the first thing I'm going to do is change that. So it's y equals 3 to the base 1/2 negative 2 bracket x minus 4 minus 1. So that means there is an a value of 3. So there is a vertical stretch of factor 3. There's a b value of negative 2, which means there's a horizontal compression of 1/2, and there is a reflection in the y-axis. H is positive 4, so there's a horizontal shift 4 units to the right. And V is negative 1, so there is a vertical shift 1 unit down. Again, this 1/2 is the base of the original exponential function. So we've already taken into consideration that 1/2 when we drew this yellow curve. So we are now going to apply A, B, H, and V. So I have described them here on the left. Feel free to pause the video if you need to take a look at those again. And again, I forgot to mention the asymptote. So just make sure you know that that is there, and the equation is y equals 0 right now. Okay, so we're going to apply A and B first. So this first point I'm going to do here is negative 3, 8. A vertical stretch of factor 3 is going to bring this point way off the grid. 8 times 3 is 24. That's going to be too far above the grid, so I'm not going to be able to plot this point. So I'm going to go to the next point here at negative 2, positive 4. A vertical stretch means that I'm now, instead of being 4 away from the x-axis, I'm now going to be 12 away. That's only 1 square up, so I'm just going to plot that above. But first I have to apply the horizontal compression of 1/2. So instead of an x value of negative 2, I'm going to have an x value of negative 1. I'm going to have the distance away from the y-axis. And then I have to reflect that in the y-axis. So the point here at negative 112 becomes 1, positive 12. So I will plot that point right there. The next point here, negative 1, 2. So a vertical stretch by factor 3 is negative 1, 6. Horizontal compression by 1/2 is now negative 1/2, 6, and then reflect it. So it's going to be positive 1/2, 6. The next point here at 0, 1, stretch that by a factor of 3, so it's going to be 0, 3. And because it's on the y-axis, the horizontal compression and reflection will not affect this point. And then finally, this last point at 1, 1/2. 1/2 times 3 is 1.5. So right now I'm half away, so now I'm going to triple that. So there's 1/2, there's 2 halves, there's 3 halves at 1.5. And then I'm going to compress that horizontally, so it's going to be here, and then I'm going to reflect it in the y-axis. So that will end up right here. So you're going to draw those points together. This is the last point that we have right here, but our asymptote has not moved. So you're going to keep coming down and hug the same asymptote. You got to get really close to that asymptote, even though our last point we had was not that close to the asymptote. And then I'll just label that equation, y equals 3 bracket 1/2 to the negative 2 to the x. Finally, we will just take all of these points on the red curve and move them 4 to the right and 1 down. So this point here above the graph at 12, when I move it 4 to the right, 1, 2, 3, 4, and bring it down 1, I'm actually back on the grid at 11. So that point goes right here. And then I'm just going to do the same for the other point. So those are the 4 points I have. Because we have a vertical translation down, this horizontal asymptote will actually be moved down by 1. So you will now have to draw in the asymptote to get full marks because it's not on the axis. and you would label that y equals -1. So there's only one asymptote in exponential functions. The only transformation that will affect it is the vertical translation up or down. So now I'm just going to hug my asymptote and go through all of those points. And then just make sure you label your equation. And finally, we can just talk about the domain and range. The domain x is still an element of all real numbers. That will not change for an exponential function. And then y is an element of all real numbers, but y is restricted by this asymptote. So that means y is greater than 1.